Hello everyone. So welcome to our video lecture session, and today we are starting with one of the most important topic with respect to board examinations as well as competition examinations, that is optical isomerism. Okay, so in our earlier video lectures we have completed conformers. So let's see what are optical isomers, why it is important to study optical isomerism, what is its application in our day-to-day life. So if I'll say a small application to understand the broad view and importance of optical isomerism, see, in medical industry, if I'll say in health sector, lots of medicines which we are using or doctors refer to the patients are actually chemical compounds. If I'll specifically say, then they are organic compounds. So those organic compounds are actually various compounds are optical isomers. Okay, see, one compound which is optical isomer, suppose I am saying a compound A and it is showing optical isomerism, so the other isomer, optical isomer of that compound will be B. So we have observed that A is having some specific activity but B is having some other specific activity. So let's start with our topic of optical isomerism. See, stereoisomerism, if I'll say, isomerism was of two types, constitutional and stereoisomerism, right? Structural isomerism and stereoisomerism. Stereoisomerism was again of two types, conformers and configurational isomerism. Now, if we see conformers was mainly due to, if I'll say conformers, it was mainly due to the rotation of free rotation across sigma bonds. Okay, or in case of rings, we have studied about chair conformers and all these things. So it is done. Now, if I say about configurational isomerism, it is further divided into geometrical isomerism and optical isomerism. Okay. Now, as we know, geometrical isomerism was further classified as cis-trans system. We have already seen the application of GI in conformers. Now it can be classified as EZ system or syn-anti system. Okay, so this was all about the geometrical isomerism. Now let's see optical isomerism. When we say optical isomerism, it is something related with optics, light, the phenomena of light on various compounds. Okay, what happens? So when we say optical isomerism, then here we need to study about enantiomers and diastereomers. Okay, the specific parts which we need to study inside optical isomerism is enantiomers and diastereomers. Okay, so let's come to our optical isomerism. Let's start. Optical isomerism. So first of all, we have to learn a few points. Okay, first thing is optics, light. If we say light, if a light source is there, suppose we say sunlight or tube light or any torch light, so from the source of light, when we observe that the light rays are having oscillations in all the directions. Okay, so they are moving in all the directions, right? But if that is simply called as unpolarized light, which are moving in all the directions in all the planes, right? But when we say that the particular light having a particular plane, that will be called as polarized light. Okay, so to make unpolarized light, into polarized light, we need a polarizer. Okay, generally Nicol prism, it is having a specific property as a polarizer, having some specific material which it is made up of, that is calcite, calcium carbonate. Okay, so that is used as a polarizer. So what happens, let's see. If simply I will say that light rays are moving in all the planes, various planes, just for simple representation I am showing with these lines. Okay, so if I use a polarizer, this is simply your Nicol prism. Sometimes you represent it like this, or many times it is simply shown like this form. Suppose simply this is a polarizer. Okay, so when light rays pass through this Nicol prism, it is your polarizer, right, made up of calcite, CaCO3 content. Then what happens, a particular plane of light is observed. See, now here it was unpolarized light. Okay, you may say it is a source of light coming through this, source of light, that may be sunlight, tube light, torch, or anything, right? So light rays are coming, unpolarized light. Now this is light rays in a particular plane, so it is called as PPL, plane polarized light. Clear? So when unpolarized light is passed through Nicol prism or a polarizer, then a particular plane of light is observed, means the light rays in a particular plane having oscillations in a single direction, right? Now what happens, we have to understand that which compound can show optical isomerism. First of all, we have to learn which compound can show optical isomerism. So if I will simply say a polarimeter tube, that simply consists of a cylindrical like vessel. Okay, cylindrical vessel having length L. Okay, now this is containing solution of any substance, for which we need to understand whether that substance, or in particular that organic compound, can show optical isomerism or not. Okay, now the length is L and the concentration of this substance here is in concentration of substance in gram per ml. Yes, you can say that here simply we are saying about the density of substance in gram per centimeter cube or gram per ml, right? Mass per unit volume. So when this plane polarized light is passed through this solution of any substance for which we need to observe, then there are two possibilities. This particular plane polarized light may be rotated after passing through this substance. So now again we need one analyzer here. See, this is again an analyzer. Analyzer means simply to analyze the light coming out after passing through this substance. PPL passed through this substance. Okay, this is your polarimeter tube, you can say polarimeter tube. Now when light rays come out of this polarimeter tube, then with the help of this analyzer it is observed. So there are various possibilities. One possibility is the way it has entered inside this tube, the same way it has come out. So here is our observer. Okay, observer eyes, you can say. So this observer is observing the light rays coming out. So first possibility is the way it has entered, means in a particular plane, it is coming out in the same plane. from this experiment we can say that the compound or that substance is optically inactive, means it is not showing any sort of optical activity. See, what does it mean, optical activity? It is having no activity or effect on plain polarized light, so it is optically inactive, or it has no optical activity. But if the light on passing through this substance is rotated in a particular direction, either clockwise or anti-clockwise, in any angle theta or say alpha, then we can say that the substance or compound is optically active. So if a substance is optically active, it is showing optical isomerism. Again, it is showing optical activity, means it is showing its effect on plane polarized light. Clear? Okay. So again, let me say, from source of light we have unpolarized light which have oscillations in all the directions. So with the help of polarizer we have found a plane polarized light, means the light is polarized in a particular plane. It is passed through the substance which is under observation, and here we have analyzer. This analyzer says about the effect of PPL with respect to the substance. If analyzer shows that PPL is same as it was earlier, means there is no optical activity. But if the light rotates in any of the direction, means there is optical activity present, means the substance will be optically active and it will show optical isomerism. So students, I think this part is clear to everyone. Everyone must have noted it down. So I think I should explain this part with a pictorial part so you can better observe and visualize in proper way. Okay, so dear students, let's observe one by one. First of all, see this image. Now what this image is all about? If you will see that this part is your source of light. Light is coming from this side and it is unpolarized light, means it is going in all the directions. It is having various oscillations, you can see. If we see the light waves, it travels like sine waves, right? So you can see this, it is traveling like this. Different directions, oscillations are there. Now this is your polarizer. Now what is the role of polarizer? If I have to get the light of in a particular plane, as per the desire, as per what I wish to get the light in a particular plane, I'll be keeping that polarizer. Okay, so you can see here, earlier the light rays were traveling in all the directions in various oscillations, but the one coming out from this polarizer is in a particular plane, in a particular orientation. You can see here, this one. So as per the direction I need, I will keep the polarizer, okay, to get a particular plane. So this is your PPL, plane polarized light. Okay. Now you can see, you could of course orient the linear polarizer in any direction. This polarizer, linear polarizer, in any of the direction, and the light would only come through in that orientation. So as per the orientation required, you will keep the polarizer. If you vertically polarized the light, see, you as per the orientation of polarizer, you can get the light's orientation. It may be vertically oriented or horizontally oriented as per your requirement. So students, I think this is clear to you. Now let's observe this image properly. See, this is your source of light. Light beams are coming here. Now you can see it is unpolarized light. It is having oscillations in various directions, and as per the orientation of the polarizer, you can observe that light rays are coming outside in a particular plane. So it is your PPL, plane polarized light. See, the source of light can be any: sunlight, tube light, torch, or whatever you wish, you can take it, right? Now let's observe perfectly what actually happens. Okay. See, a source of light is taken initially, first of all, and it is traveling in all the directions. Light rays are having oscillations in all the directions, right? As per the electric field and magnetic field perpendicular to each other, the light rays are having oscillations. So the normal light is having oscillations in all directions. You used polarizer, that was your Nicol prism. See, again and again I am repeating the things. Why? Because such things comes in MCQ pattern, right, in competition exams. So you need to remember everything. Polarizer is Nicol prism. Now we got plain polarized light. Okay. Now here I am telling you one important concept. See, if a compound is optically active, means if it is showing optical activity, so it must be having some particular rotation, that is called specific rotation. Okay, means when that substance is passed through plain polarized light, then we know we have substance are fixed. Suppose I am keeping here 2-butanol. Okay, simply if I say CH3, CH2, CH, CH3, this is OH. So this is your 1, 2, 3, 4. This is butane to all, okay, or 2-butanol. So if I keep this compound, so once the compound is fixed, correspondingly, if I say that this compound is optically active, means the rotation which is caused due to this compound will also be fixed, right? So you can see here, when PPL is passed through the sample tube containing a chiral compound. Now here one word is used, chiral. Okay, we will discuss it in detail. Chiral. Okay, chiral compound. Now what is this chiral? Chiral means unsymmetrical. Now you have to understand why the compound shows optical activity. So the condition is, if the compound is unsymmetrical, then it will be chiral. So chiral compound is unsymmetrical compound, and the reverse, achiral compound means symmetrical compound. So any compound which is chiral, okay, that will show optical activity. So sample tube containing a chiral compound. So if I have fixed that the compound is chiral, means it must show optical activity. So it will definitely rotate the plane of polarized light. Okay, so you can see here the light rays are rotated in a particular direction, that may be clockwise or anti-clockwise. So with the help of analyzer, the viewer can observe it. Okay, is it clear? Right, I think you are clear. Let me show you one important observation with respect to this phenomena. When unpolarized light is polarized first using polarizer and sample tube containing organic molecule, I said the length of the tube will be L in decimeter. Remember the unit. We have to fix the limit, right? Units. So this length of tube is in decimeter. Okay. We know 1 decimeter equals to 10 centimeter. Decimeter is simply 1/10 of meter. So that is simply 10 centimeter. Okay. Now the solution organic compound having concentration gram per ml. Okay. Now it is saying specific rotation 30 degree. Now what does this mean, specific rotation? Specific rotation simply means the amount of rotation or the angle of rotation of PPL, okay, in this polarimeter tube experiment or polarimeter experiment caused when the length of the tube was 1 decimeter and the concentration of solution was 1 gram per ml. Means specific rotation means the rotation of a compound, rotation of PPL when passed through this experiment having angle of rotation here as per this 30 degree when the concentration is 1 gram per ml and length is 1 decimeter. Okay. Now this light is observed in a particular direction. As we have already told, specific rotation is there. So movable analyzer which observes. Now we have two cases. the light can be rotated in clockwise direction or anti-clockwise direction. Okay, so there are possibilities. Light can be rotated in clockwise or anti-clockwise. Okay, accordingly, the substance which rotates the PPL can be named in two different ways. If a substance is rotating the PPL on clockwise direction, then it is called as dextrorotatory substance. So if it is clockwise, then it is said as dextrorotatory substance, which is represented by small d or plus symbol, plus. Okay, now if a substance rotates the PPL in anti-clockwise direction, then it is represented by minus symbol or levorotatory. Levo means simply left, okay, and dextro is simply right, clockwise, represented by small l or minus symbol. So here I used two different terms, dextrorotatory and levorotatory. So if PPL is rotated in clockwise, dextrorotatory; if it is anti-clockwise, levorotatory. Okay, for small d, I am saying small d and small l. Remember these terminologies: small d or plus, small l or minus. Okay, so I think it is clear to you all. So dear students, what I discussed till now was about rotation of plane polarized light. So we need to understand two things. First of all, sir, how will I understand that which compound will rotate PPL and which compound will not rotate PPL? So first thing is, it is experimental. Firstly, I am discussing the experimental part, how it is done, right? Then we will come to the theoretical part, that by observation or by just saying the name of the compound or structure of the compound, I can analyze whether it is optically active or inactive. Okay, so if I will show you the experimental setup, so this is the perfect setup which is used for optical activity. This is your cylindrical vessel type, okay, polarimeter tube, and this experiment is overall called as polarimeter experiment. Clear? Remember this word, polarimeter experiment, where you have polarizer, you have analyzer, you have PPL, and you have this polarimeter tube having length L, concentration C. Okay, angle of rotation of plane of polarization, this analyzer. Okay, so this is your setup, overall setup. Now let's come to the theoretical part. Let's start our theoretical part, how to observe a compound is dextrorotatory or levorotatory in detail. Okay, so students, see, here I have taken one substance. This carbon is having bromine, chlorine, fluorine and hydrogen, means simply CH, F, Cl and Br. Okay, so here also carbon is having H, F, Br and Cl. Now if I will observe these two compounds, then one compound is your hydrogen and fluorine. It is in the plane of this board, and as we have already discussed wedge and dash form, so you know dash form in backside of the plane and wedge form in front of the plane or towards you, right? So this chlorine is towards you, this bromine is backside of the plane, away from you. This fluorine and hydrogen and carbon, these are in the plane, okay, in this plane only. Now if I will see, this is your first part, this first one, this is your first. Now this is your second, carbon. Now see what has been done. If I will see hydrogen, fluorine, it is again same, but now what has been done, if you observe here bromine was backside, but in this bromine is front side. Here chlorine was front side, here chlorine is backside. So if I will simply observe, then on keeping one mirror in front of this compound, we will get this compound. So simply it can be observed as the mirror image of this compound. Okay, so these two compounds, on observation we find that this PPL plane polarized light. On passing through this compound, it rotated. If I will simply observe this side with respect to this PPL, it is observed this side. So this angle alpha, okay. So it is clockwise direction. So what we say to clockwise direction, that is your dextro-rotatory substance, okay, represented by small d or plus. So this substance is our dextro-rotatory substance, okay. Now if we observe this one, so you can see here with respect to straight PPL, with respect to PPL, it is observed here anti-clockwise. Again, one question arises, sir, the compound is same, structural formula is same, only optical activity, means the rotation of PPL is occurring due to different spatial arrangement of atoms in space. So what will be the angle of rotation? So I cannot say what will be the angle of rotation because it is fixed for particular compound at particular temperature. See, it is dependent on temperature. The specific rotation will depend on temperature as well as the wavelength of light. Temperature dependency as well as the wavelength of light in nanometer we can say, means which wavelength of light has been used for this experiment. It depends on these two things as well as the length of tube and concentration. So you can say the angle will be a particular angle, but the difference in these two will be only difference that if this compound rotates the light in clockwise direction in an angle alpha, say if I am saying here theta, then I can say the same compound which is mirror image of this one, which so it will rotate in anti-clockwise direction and the angle will be minus theta, okay. The only difference with the same compound which are mirror image of each other, if it rotates in clockwise, it will rotate in anti-clockwise. If it rotates theta angle, it will be rotating minus theta angle. Clear? Okay. So this is your levo-rotatory substance represented by minus symbol or small l. Okay, so dear students, note it down and let's continue the topic. So let's see factors in which amount of optical rotation of PPL depends. So there are some particular factors which you have to remember on which the rotation of PPL is dependent, okay. So first thing is temperature. Simply if I represent here by small t in degrees Celsius, okay. Second, wavelength of light used, so it will be also dependent. Here if I say it in lambda nanometer, okay. Third thing, first thing is temperature, second thing is wavelength of light used, third thing is concentration or density of substance or solution. It is represented by C, unit is gram per ml or gram per cc, centimeter cube, that is same. And last thing is length of tube, or it may be also said as the length up to which PPL is passing through. Means as per the polarimeter experiment, more the length covered if the compound is optically active, the more will be rotation, okay. Again, more will be the concentration of solution, more will be optical rotation of PPL if compound is optically active. So length of tube or length up to which PPL has passed through that is simply your d, distance, or simply you can say also say, or L, better to say L here, length. Okay, L in decimeter, right? So these are the four factors in which optical rotation is dependent. So now let's learn what is a specific rotation. Specific rotation. So students, specific rotation simply means it is the amount of optical rotation of plane polarized light on passing through optically active substance having concentration 1 gram per ml in a tube having length 1 decimeter. Okay, so if I simply say alpha, it is specific rotation at a particular temperature when lambda, wavelength of light in nanometer used is lambda, that is simply represented by alpha naught, or I am saying alpha observed rotation per unit length per unit concentration. Okay, so students, specific rotation is the observed rotation or optical rotation. It is observed rotation at per unit length and per unit concentration in gram per ml and length in decimeter. Okay, now you have to understand, for a particular compound specific rotation is fixed. So what happens if I am saying the length of the tube is increased, means the distance traveled by ppl is increased. So more the distance increment, more will be the variation from plane of polarized light, means more will be the optical activity or more will be the rotation in clockwise or anti-clockwise direction as per the optically active compound. Again, more will be the concentration, more will be observed rotation. So if the length L or concentration C changes, alpha naught also changes, but alpha, that is your specific rotation, that remains constant. Okay, or in another terms you can say that observed rotation for any compound or any solution equals to the specific rotation of that substance into length into concentration. Okay, so for a particular experiment, if you have taken particular length L, concentration C, and you know the specific rotation, that will be given, so you can observe or calculate the alpha observed rotation. Okay, optical rotation. I think everyone has noted this. Okay, cause of optical activity. Now let's understand what is the cause of optical activity. If a compound is showing rotation of plane polarized light in any of the direction, then it is optically active substance. But what is the cause? Why a particular compound can cause optical activity? So the only reason is, if any compound is chiral, then it will show optical activity and it will form optical isomers. Okay, so the reason is, if the compound is chiral, as per the meaning chiral, unsymmetrical, then it shows optical activity. Okay. Again, if I say chiral, it means unsymmetrical. So if I'll say compound is achiral, if a compound is achiral means symmetrical, means no optical activity. Okay. Any compound which is chiral will show optical activity, rotation of ppl, but if a compound is achiral or symmetrical, it will not show any optical activity. Clear? Okay. See, we earlier used, in various cases, we use the term rotational energy barrier. Rotational energy barrier. So let's take out this point to correlate the entire thing which we have studied. Okay. So I'll just relating rotational energy barrier to the particular cases where we need this term. So first thing was functional isomer. Okay. Tautomerism. Conformers. Functional isomer, tautomerism, conformers, and last geometrical isomers. Now let's understand here what is the relation. When we say functional isomer, they are actually very different compounds. The two compounds are very different, right? So in case of functional isomers, the rotational energy barrier is very high, right? We cannot rotate it easily. The rotational energy barrier is very huge amount. Now when we say tautomerism was one sort of functional isomer only. They are real species. They can be seen and they can be separated, can be seen and can be separated. Now when we say conformers, we have observed that they can be seen. They can be seen as two different conformers, but can't be separated. Okay, they have very less rotational energy barrier. But when I say geometrical isomers, in geometrical isomers there is restricted rotation. You cannot rotate it. So there will be very high rotational energy barrier in case of geometrical isomers. So it is one type of configurational isomer only. Okay. Now here, if I say optical isomerism, so geometrical is due to restricted rotation and optical isomerism is due to rotation of plane polarized light. So there is nothing about bond rotation. It is about rotation of plane polarized light in clockwise or anti-clockwise direction. Okay, so I think it is clear to you. How to check symmetry in any compound? So dear students, there are various elements of symmetry in any compound. Okay, out of which we will be studying various types of symmetry through which we can observe whether the compound is active or inactive. Means if a compound is symmetrical, it is having any one of the symmetry which we will discuss here. Apart from that, there are various cases, but we will see here 4 particular types of symmetry. First is plane of symmetry, second center of symmetry, third axis of symmetry, and fourth alternate axis of symmetry. Okay, if I say plane of symmetry, means with respect to a particular plane we have to observe. We will discuss it in detail. It is simply represented by sigma. If I say types, then it is sigma horizontal, sigma vertical, or sigma diagonal. For plane of symmetry, we also use molecular plane. Molecular plane. Now let's say center of symmetry. Center of symmetry is represented by Ci, or it is also called as center of inversion. Okay. Now when I say axis of symmetry, it is represented by Cn. N is for angle. Okay. N. We'll discuss it. And when I say alternate axis of symmetry, it is represented by Sn. Okay. So just note it down. So dear students, these types of symmetry, once we discuss, we'll come to know which compound is symmetrical and which compound is unsymmetrical. Accordingly, we can say which is optically active, which is inactive. But first of all, let's see its day-to-day life observation. I'll show you with respect to some particular compounds how it is affecting us. Okay. So students, here I am showing you two compounds. See, this compound is Darwan. Okay. And this compound is Novrad. Now, if you will see the structure of these two compounds, you will find that this carbon is having benzene, CH2 benzene. Carbon is having CH2 benzene, benzene. And this is having OCOET. This is having CH, CH3, CH, CH3. And this side is your CH2 and CH2 and 2-methyl. Means the two compounds are actually exactly similar. So what differs here? These two are actually mirror image. As said, see here you have placed mirror, so they are a mirror image of each other. From observation, it has observed that two compounds are optically active. Now I am not discussing with respect to symmetry. I am just telling these both rotates PPL in different direction. If it is in rotating the PPL in clockwise, then it is plus or D. Then correspondingly I can say this will be minus or L. Now what is the observation? In daily life, this Darwan is observed as an analgesic. This compound is observed as an analgesic. If you will see in terms of medical practitioner, analgesic in simple terms is simply your painkiller. Okay. This compound Darwan is used in medicine industry as a painkiller. But the same compound, just due to optical activity or just due to difference in spatial arrangement, the application differs in Novrad. It is antitussive, or in simple terms, if I will say, it is used as anti-cough agent. Okay. Means if you have allergies or cough and cold, in that cases, this compound is used as a medicine. Okay. So you can see it. I have simply here mentioned the names, just like we used in geometrical isomerism EZ. Here we will be using the terms RS configurations. Okay, R and S. In geometrical isomerism, we used EZ configuration. Here we will be using RS configuration. See, you can see this compound is 2S3R proxyfen, and this is 2R3S. See, 2R3S and 2S3R. Just due to this change in configuration, the activity and the application of the two compounds is different. Novrad is antitussive, while Darwan is analgesic or painkiller. Okay. So guys, if you see these two compounds, actually this is same, right? But what difference lies in this compound is, you can see it has mentioned plus limonene. Okay, so this compound is optically active. It is showing optical activity with clockwise rotation of PPL. So it is plus limonene, or simply you may represent it as L limonene, while this compound is your minus, so you may say it as L limonene. Now why I am showing you these two compounds? To make your observation clear towards optical activity. It has been observed in these two compounds that they are widely used in medical field on discovery of various medicines, in terms of fragrance, in terms of sweetener, and all these cases also they have various applications. I am just saying you a small example. It has been observed that this plus limonene is found in orange flavoring part, but this minus limonene is found in your lemons Okay, so when in terms of order and taste, if you will see that they have difference just due to their optical activity. See, this is the compound. If you will see this compound, then from this carbon it is having chirality. So students, I think everyone has understood what is optical activity, how PPL gets rotated. So we'll discuss it and continue it in our next lecture. We'll continue with the topic of symmetry of elements, how to decide which compound is symmetrical or unsymmetrical. Okay, so see you in next video lecture.